Okay, let's dive right into this explainer and build a rock-solid foundation on how GPUs actually work. Look, if you're an AI engineer, you already know that your hardware choices completely dictate your project's limits, right? So today, we're taking a journey. We're going to move from basic CPU and GPU concepts all the way up to a heavyweight comparison of three incredible pieces of engineering: the consumer flagship RTX 5090, the reliable A100, and the massive H200 NVL. We're pulling directly from their architectural white papers to break down exactly what makes them tick. Let's get into it.
To understand why GPUs even exist in the AI space, you really need this mental model. Think of a CPU as a highly skilled manager. It handles one really complex task at a time with incredibly low latency. A GPU, on the other hand, well, that's like a massive factory. You've got thousands of smaller workers executing the exact same mathematical operation on huge data sets, all in parallel. And since AI models require literally millions of matrix multiplications, this parallel factory setup maps perfectly to the workload. We've got some really fascinating ground to cover today. Here is our progressive syllabus. 1. Foundation. 2. Architecture and terminology. 3. Precision modes. 4. Parallel mechanics. 5. Scaling with interconnects. And finally 6. The ultimate comparison.
Starting off with Section 1, Foundation, Terminology, and Context. Let's get our vocabulary straight before we ever look at a spec sheet.
First up, what actually is an architecture? Basically, the architecture is the foundational blueprint of the silicon. It's the design family. Names you've heard like Ampere, Hopper, or the brand new Blackwell. It dictates how the cores compute. But here's the catch. The architecture name alone doesn't actually tell you what the final product looks like, or even who it's built for.
And that's why it is absolutely crucial to separate the blueprint from the actual product family. You can have an RTX 5090 and a massive data center accelerator that both utilize incredible Blackwell technology, right? But they are packaged for totally different workflows. One is a GeForce product for your desktop, and the other is built for giant rack-scale server deployments. Same underlying blueprint, completely different purposes.
Which brings up another major point of confusion: the chip versus the card. The chip, or the die, just contains the actual silicon compute logic. But you can't just slap a bare chip into your workstation. The card, or the module, is the complete product. It's the whole shebang. It surrounds that chip with memory, power delivery, cooling, and your I/O connectors.
Now looking at NVIDIA's architectural timeline, you can see this clear progression from Pascal through Volta, Turing, Ampere, Ada, and now Hopper and Blackwell. And this progression isn't just about raw speed. It's a relentless evolution toward better compute efficiency. A huge part of this has been the introduction and the continuous refinement of tensor cores over the last few generations, which are specialized entirely for the specific matrix math that AI demands.
All right, Section 2, Evaluating the hardware. What actually matters when you're looking at these things?
If you're an AI engineer, this right here is your true checklist. Because listen, a GPU with thousands of cores is still going to stall out if it's bottlenecked by narrow memory bandwidth, or if it doesn't have the specific mathematical precision support your model needs. You have to rapidly assess memory, tensor cores, precision formats, and scaling capabilities like NVLink. It's the full package that counts.
So let's talk about precision support, because it's vital. Precision just dictates how numbers are represented inside the GPU. Integer formats like INT8 and INT4 are beautifully compact. They take up practically no memory and run amazingly fast, which makes them perfect for efficient model inference. On the flip side, you have floating point formats like FP16, FP32, or FP64. These handle the complex fractional values and the much wider ranges you need for deep model training and scientific simulations.
Navigating these formats as an engineer is really all about trade-offs. Check out this table. You might want the sheer speed and low memory pressure of an FP8 format for modern LLM training, right? But that requires really careful numerical scaling. Or maybe you absolutely need the bulletproof numerical stability of FP64 for a high-performance simulation, but you have to accept that it's going to be slower and way heavier on your memory. Nailing the right precision is how you get your GPU running at peak efficiency.
Moving into Section 3, Parallel Mechanics, specifically SIMT and warps. Let's zoom in to the microscopic level.
It all comes down to SIMT, single instruction, multiple threads. Guys, this is literally the secret sauce of GPU computing. It allows a single command to manipulate vast amounts of different data at the exact same moment. Instead of telling one worker to do one math problem, you're grabbing a megaphone and broadcasting one instruction to an entire block of workers simultaneously. So when you're training an AI, you are basically flowing through these 4 precise steps. First, you slice huge matrix multiplications into smaller, manageable tiles. Next, you load those tiles into the GPU's shared memory. Then, you parallelize the work as groups of threads, which we call warps, operate on those tiles, constantly feeding the data into those specialized tensor cores to churn through massive multiply-add operations at lightning speed.
Okay, Section 4, Scaling Up and the Power of Interconnects. What happens when your model is just too big for one GPU?
Well, this is where the interconnect becomes honestly just as important as the GPU itself. PCIe is your standard connection. It's great for general systems, sure, but it has higher latency because it forces traffic to go through the host CPU. NVLink, however, is a specialized, high-speed, low-latency bridge. It lets multiple GPUs completely bypass the host and share tensor data directly with each other, basically making them act like one giant unified superprocessor.
To really put this into perspective, according to the product briefs, an H100 NVLink using NVLink hits a staggering 900 gigabytes per second of bidirectional bandwidth. Think about that for a second. 900 gigabytes per second is like transferring hundreds of full high-definition movies in literally a single heartbeat. When you're training a massive language model across multiple GPUs, that kind of peer-to-peer speed is absolutely mandatory so you don't hit a massive bottleneck.
And now, Section 5, the ultimate comparison. Desktop versus data center. Let's put all of this into practice. Side by side, you can instantly see the difference in scale and intent here. The RTX 5090 brings incredible speeds using 32 gigabytes of the new GDDR7 memory, pushing nearly 1,800 gigabytes per second. The older A100 totally holds its own using the Ampere architecture and HBM2 memory. But then look at the H200 NVL. It completely changes the game. Using Hopper architecture, it packs 141 gigabytes of cutting-edge HBM3E memory, pushing a massive 4,813 gigabytes per second. No contest.
Let's look a bit closer at the RTX 5090. This thing is an absolute beast for local desktop workloads and enthusiast creators. It leverages the GB202 Blackwell architecture, along with 5th-gen tensor cores. But one of its coolest features is introducing FP4 and FP6 precision support. That drastically reduces memory usage when you're doing local AI inference. It's built for the workstation under your desk, not a server rack.
Conversely, you've got the A100 and the H200 NVL, which are designed from the ground up for massive data center scaling. Both of these utilize MIG, that's multi-instance GPU, meaning you can partition one single GPU into up to 7 completely hardware-isolated instances. The H200 pushes just massive throughput for modern FP8 workloads, and both rely natively on that high-speed NVLink infrastructure we just talked about to train the world's largest models.
So here is the crucial point, your practical checklist. Before you ever pull up another spec sheet, ask yourself, evaluate your specific memory needs. Do you really need the 141 gigs of the H200, or will the 32 gigs on the 5090 totally suffice? What precision formats are you relying on? Are you just testing locally, or are you deploying a massive server rack where NVLink is pretty much mandatory?
I'll leave you with this final thought to ponder as you design your next AI system. Based on the exact mechanics we've uncovered today, from how those tensor cores chew through the math to the sheer volume of memory bandwidth, which of these architectural marvels is the true perfect fit for your workload? Thanks so much for joining me on this explainer, and I'll catch you in the next one.